Hey guys, welcome back to Edgeverse. Or if you're new here, hit that subscribe button right now because we're diving into one of the coolest stories in physics history. Imagine this. Everything you see around you, the colors in the sky, the way magnets stick to your fridge, even how your phone screen works. All of it boils down to a tiny property of electrons that no one knew existed until the 1920s. It's called electron spin. And get this, it's not even real spinning like a top. It's a purely quantum weirdness that changed physics forever. But how did we discover it? Why did it take so long? And why did some of the biggest names in physics initially think it was nonsense? Today, we're unpacking the full story, from mysterious lines in atomic spectra to a groundbreaking experiment that split a beam of atoms in two. Stick around, because by the end, you'll see why electron spin is the hidden hero behind modern tech like MRI machines and quantum computers. Let's start at the beginning. Back in the late 1800s and early 1900s, scientists were peering at light from atoms using spectroscopes, and they noticed something weird. Take the hydrogen atom, the simplest one. Niels Bohr's model in 1913 nailed the big spectral lines, like the famous H-alpha line at 656 nanometers. But zoom in with better tools, and that single line? It's actually split into multiple closely spaced lines. This is called fine structure. And it wasn't just hydrogen. Sodium's famous D-lines? Doublet. Elements across the periodic table showed these extra splittings. Bohr's model couldn't explain it. Something was missing. Then there's the Zeeman effect. In 1896, put an atom in a magnetic field, and its spectral lines split even more. Classical physics predicted nice, even patterns, but often weird, irregular splitting called the anomalous Zeeman effect. Lines splitting into odd numbers, spacings that didn't match theory. Physicists like Wolfgang Pauli were obsessed with these anomalies. They screamed that our picture of the atom was incomplete. Arnold Sommerfeld tried to fix Bohr's model by adding elliptical orbits and relativistic effects. It helped explain some fine structure, but not everything. The anomalous Zeeman? Still a mystery. So, what was going on inside the atom? Fast forward to 1922. Two physicists, Otto Stern and Stern-Gerlach, set up an experiment that would blow the doors open. They shot a beam of silver atoms through an uneven magnetic field. Classically, the atoms should have random orientations, so the beam should smear out on the screen, like a blurry line. But what they saw? The beam split cleanly into two distinct spots. Nothing in between. This proved angular momentum is quantized. It only comes in discrete chunks. At first, everyone thought it was orbital angular momentum, like the electron looping around the nucleus. But here's the twist. Silver atoms in their ground state have zero orbital angular momentum. So why the split? The answer was coming. Around the same time, Pauli figured out his famous exclusion principle. No two electrons can have the exact same set of quantum numbers. To make the periodic table work, there had to be a fourth quantum number, and it only had two possible values. What could that be? Something with just two states. Enter two young Dutch physicists in 1925, Samuel Goudsmit and George Uhlenbeck, working under Paul Ehrenfest at Leiden University. They proposed something bold. The electron has its own intrinsic angular momentum, separate from orbiting. They called it spin. Value, half a unit of h-bar. And it can point up or down, exactly two states. This explained Pauli's fourth quantum number perfectly. Suddenly, everything clicked. Fine structure? From spin interacting with orbital motion, spin-orbit coupling. Anomalous Zeeman now includes spin's magnetic moment. And Stern-Gerlach? It was measuring spin, not orbit. But not everyone was convinced. Pauli himself hated it at first. How can a point particle spin? It would need infinite speed at the surface. Plus, early calculations showed the magnetic moment was off by a factor of 2. Actually, another physicist, Ralph Kronig, had the same idea months earlier, but Pauli shot it down, so he didn't publish. Thankfully, Ehrenfest encouraged his students. Goudsmit and Uhlenbeck went ahead and published The Factor of 2 problem, solved in 1926 by Llewellyn Thomas. He accounted for a relativistic effect called Thomas precession, basically frame-switching weirdness when the electron orbits. Add a half factor, and boom, perfect match with experiment. Then, the ultimate vindication, Paul Dirac in 1928. He combined quantum mechanics with special relativity from first principles, and spin popped out automatically. No need to add it by hand. Plus, his equation predicted the exact magnetic moment and even antimatter. Skeptics, including Pauli, came around. Spin was here to stay. So, why does this matter to you and me? First, the periodic table. With spin, each orbital holds 2 electrons. That's why elements fill shells the way they do. Explains chemistry completely. Chemical bonds? Covalent bonds rely on paired opposite spins. Magnetism? Ferromagnets like iron-aligned spins. In modern tech, MRI scans flip nuclear spins in magnetic fields to image your body. Spintronics for faster electronics. Quantum computers using spin qubits. All from this discovery. What I love about this story, it shows science isn't just lone geniuses. It's collaboration, mentorship, and pushing through skepticism when the idea explains too much to ignore. It also reminds us quantum world defies intuition. Electrons aren't little spinning balls. They have this abstract spin property with no classical analog. So, there you have it, the wild journey to discovering electron spin. From puzzling spectral lines to revolutionizing physics. What do you think? Was spin the biggest quantum surprise of the 20th century? Or is there something even weirder? Drop your thoughts in the comments below. I read them all. If you enjoyed this deep dive, smash that like button, subscribe for more physics history and explanations, and hit the bell so you don't miss the next one. Thanks for watching, and I'll see you in the next video.